Okay, number 2 and number 3. Before I work out number 2 and number 3 with you guys, I want to say something really important about static equilibrium situations. Guys, anytime it turns out that anytime you have a system and you know that system is in static equilibrium, basically what that means is that that system is not accelerating. Okay, so for example, consider this traffic light here. So this traffic light is hanging from 2 wire cables, and as the traffic light just sits there, it's obviously at rest, so it's not accelerating, meaning it's in static equilibrium. And guys, it turns out that it is always true that any time that you are in static equilibrium, it is always true that the sum of your forces in the x direction is equal to 0, and the sum of all of your forces acting in the y direction is also equal to 0. Okay, and that's true for any situation that is in static equilibrium, meaning the system is not accelerating. So, for example, in this case of the stoplight, what are all the forces that are acting on the stoplight? Well, obviously, there's a force of gravity acting straight downward, right? Because this stoplight is acting straight downward. And there's also the tension from these cables here. So, this cable is pulling with a tension force in that direction. And this cable right here is also pulling with a tension force acting in this direction. Okay. Now, it turns out that these cables, since they're acting at an angle, I can split up these vectors into their x components and their y components. And I can also do the same thing for this right here. Split it up into its x component and its y component. And so when I do that, all of my forces acting up in the x direction must be equal to 0. And all of my forces acting up in the y direction must also be equal to 0. So that is true of any system that is in static equilibrium, meaning it is not accelerating. So with that said, okay, let us look at number 2. Which of the following statement below is always true of a system that is at equilibrium? Okay, well, if it's not accelerating, that means the system is maintaining its current state of motion. So it could be B. So B could be a statement that's always true. Well, no, I'm sorry. It is always true that the system is maintaining its current state of motion, because if it's not accelerating, it could either be at rest or it could be moving at a constant velocity. Okay. So see, the system's velocity is not changing. Okay, this is always true for a system that is in static equilibrium. D, the net force on the system is 0 newtons. We just said this. If you add up all the forces acting on your system, your net force must be equal to 0. And I just said this. E, the system is not accelerating. And lastly, F, the individual forces acting on the system are balanced. Okay, so all of these statements are always true whenever we're in static equilibrium. Now notice A is not always true. I mean, it could be true, but not only is the system that's at rest also in static equilibrium, but it could also be true that the system could be moving at a constant velocity. Okay. So let us look at 3. 3 says, the following statements below were made about a system. In which case could you conclude that the object is at equilibrium? So in which case could you conclude that? Okay, well, look at A, the system is at rest. That's something you can conclude. If you know the system is at rest, you know that, you can conclude the system is at equilibrium. What about B? The system is moving at a constant velocity. That's something you can also, well, if it's moving at a constant velocity, you can also conclude that that system is in equilibrium. What else? Okay, so look at C. The object is moving. Just because an object is moving, can we conclude that that system is in equilibrium? No, we can't conclude that, because the object could be moving and it could be accelerating. The object is moving at a constant speed. Now, this is a kind of tricky one, because something can be moving at a constant speed while at the same time changing directions. So, for example, if something is moving in a circle, and we're going to talk more about this when we get to circular motion, it can be moving at a constant speed in the circle, but it could also be changing directions. So if it's changing directions, then that means its velocity is not constant. So in which case, if its velocity is not constant, we can't conclude that that system is at equilibrium. Let's look at E. The system is stationary. Well, yeah, if we have a system that's stationary, meaning it's at rest, we can definitely conclude that that system is in equilibrium. So we can circle E. The acceleration of the object, or the acceleration of the system, is 0 meters per second squared. We can also conclude that. And lastly, G, we can, if we have a system that's, the individual forces acting on the system are balanced, if that's the case, then we can also conclude that the system is in equilibrium. Okay, so those are all your answers for number 2 and all your answers for number 3.